Hi guys, today we'll be solving problem number 69, so finding the square root of a value, integer value x. So the x is a non-negative integer and it's given to us, and we want to return the square root of x rounded down to the nearest integer. So we are not allowed to use any built-in tools such as power in C++ or double asterisk in Python. Now, if you look at the example, the problem statement is pretty simple. You are given x and we want to find the output. Well, the first example is pretty straightforward, but in the second second example, x is 8 and the square root of 8 is 2 root 2, I believe, and the output is 2. And the explanation is that the square root of 8 is in decimal 2.82, but since we are rounding down to the nearest integer, the answer is 2. Now, since this problem is also a binary search problem, we can solve this using binary search method. But first of all, I'd like to solve this using normal method, which has the complexity of O of n. That way, it's much easier to understand the binary search method. So this is the solution which has complexity of O of n. You can see a while loop that runs while the I squared is less than and equal to or equal to x. Now if we consider I to be the square root of x, then if we square the I, then it should be exactly equal to x. But in this problem, we are looking for square root or nearest rounded down version of that square root. So anything less than or equal to x is a fine solution as well. And inside this while loop, all we are doing here is incrementing the value of I. And basically what we are trying to do is iterate I from 0 all the way until that I square is at least greater than x. And finally we are returning I minus 1. This is because just imagine that I squared equals to exactly x at any given value of I, and even in that situation we are incrementing the value of I by 1. We want to undo that change by subtracting by 1, and that's why we have a subtraction here. And this solution should work. This should pass all the test cases, just that it is a bit slow. If I submit it, you can see that it is a right solution, and our solution is very slow, much slower than rest of the solutions we have. We are taking almost a second, but this solution should be solved much faster, and for that we have to use binary search tree to limit our search space. Another solution in a sublime text, and this solution uses binary search tree. If you look at the solution, we have first initialized the left and right pointers, which is initialized to 0 and x. This is because our solution exists within these boundaries of 0 and x. We have also initialized a new variable called answer, which holds the square root of x. And then we have a loop that continues as long as left is less than or equal to right position. And we have also calculated the mid position, just like in normal binary search tree. And we have conditions to check. The first condition is if the square of mid is less than or equal to x, it means that our solution is on the right side of the search space, or the solution exactly mid position. So if that's the case, then we want to update our left pointer. We want to shift the left pointer to the right, and to do that what we've done is that initialize left with the mid plus 1 position. And also we have assigned mid to the answer because mid is a possible candidate to be the square root of x. That's why we have assigned mid to answer. We also have a else condition. This runs if the square of mid is greater than x. In such case, the solution is on the left side of the search space, so we want to update the right pointer with mid -1 position. And this loop runs until we find the best possible candidate for the square root, which will be assigned to answer, and that's what we are returning from this function. So if we run this code, you can see the square root of 4 is 2. That makes sense. If I run the square root of 8, this should also return 2. But if I put 9, it should return 3, and which is as expected. So if I copy this solution and then try to run this, passes all those test cases. Let's submit. And as you can see, the solution is much faster than previously. It ran in 0 milliseconds, so that's impressive.